All right, guys, let's take a look. So, what would n be in this problem? 44, good. So n is always the total number. Thank God that letter n is always the same exact thing. The total number that you're looking at. 44. What's p? Beautiful. Be very careful. I said this earlier, but I don't know if you really understand what I mean. Percentages were completely made up by humans. So was math, for that matter. I know that, but still, percentages aren't actual numbers. You got to take them back to their decimal form before you throw them into a formula. Otherwise, you get these weird answers. 8 billion% chance of something happening might be a problem somewhere. What must Q then be? Yeah, 1 minus this, so 0.848. Fullness. And now, like so much math, once you learn the idea behind a formula, it's just plug and chug after that. So I want probably that exactly 7 smoke. So what's going to, now watch this, let me make it really clear. For this problem, for this given problem, and all of this is related to this number 1, right? This number 44 will never change. This 0.152 will never change. This 0.848 will never change. They can't. Just because you take 5 people versus 20 doesn't suddenly change the probability that a San Diegan smokes. They're not out there smoking. I don't want to smoke anymore. Just because I picked 5 people. No. You guys with me? The only thing that changes is the X, which is why we call it X. And that changes this other dude too, because it's related to X, right? So I want 7 successes. 44 choose 7. So what's going to be 0.152 to the what power?
7.
Good. So I want to choose 7 to be successes. So of course I have 7 successes. I know that's kind of repetitive, but it's better than not. It's just out of nowhere. It's going to. And then so how many failures must I have?
37.
The rest. So this would be officially 44 minus 7. So that's 37. I like it. Holy crap, that got really bright. So that's just a 37 of 37. This is 44 minus 7. That's 37. That's why it says n minus x here. You see that? Okay. Oh, by the way, I was going to do this in a minute, but I forgot I had it on here. This is the official formula for the probability. This is what we keep doing, right? I got a total number, choose so many. So I got this many successes. Now this is where people freak out. But if I have x are successes, then n minus x would be the rest. That's the leftover. So the formula makes it look like it's worse than it really is. It's just the powers have to add up to be the total number. So what do you guys get when you put that in your calculator?
0.1611.
0.1611?
Yes.
That does sound familiar. I like it. Alright. But probably that none of them smoke. So again, the 44 doesn't change, the 0.152 doesn't change, the 0.848 doesn't change. I want nobody to smoke, so no successes. So no successes, and how many failures?
44.
All of them. I like it. In this case, I would rather be a failure. I just think, thankfully I never started smoking. It's hard. So if you do 44, you're going to get something really small, I think. Can't remember now. Oh yeah. So you get 7, on his calculator it says 7.069 blah 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 times 10 to the negative 4.
How do you...
Oh.
Well, if you were to ask us to write like...
Oh yeah, so with probabilities you always want to go 4 places. I don't know if you picked up on that. The probability quiz, 4 places. So we're always going to do probability 4 places because pretty soon we're going to use this chart to look things up. And it has all the probabilities to 4 places. So I just want us used to that.
So we just...
So then I can say this will be 0.1237. Because this one goes back 4 once and then 3 zeros. I like it. I like it. Please, dear God, if you forgot about your science civilization, please come see me. All right, this is going to happen every now and again. And then this is exactly what you should have done on 3C from the quiz. I think it was 3C. We already did this. What's the opposite of at least 1?
None.
None. We just calculated probably none is 0.0007, 0007. Is that what you said? I had this whole thing in my mind about 007, 007, whatever. And that, of course, is what? 9993. So if 44 San Diegans just randomly showed up somewhere, just randomly, I would, there's a really high probability that at least one of them smokes. So as a planning aid, I have to make sure that there's a place for them to go, so they don't go crazy and hurt people. If you smoke, I'm sorry, I'm not trying to generalize, but you need to smoke, so you need some place to go. Does that make sense? I mean, this kind of thing can be used for planning purposes. Like I said, with the left-handed, and making sure there's enough chairs in a room for left-handed people, you can do it based on what we're doing now. This is what actually happens in the real world. It's insane. All right. Here comes beautiful little formulas, right? I got 44 people, 0.152 chance of smokers. So what do I get? 6.88. Right there. And then the standard deviation. You can put in there P, NPQ, that's fine. Just realize that you've already done NP right there. If you do all that square rooted, what do you get? 2.382?
Yeah.
Is that what you guys got? Crowdsourcing this. Alright. So they still mean the same thing they always have. The mean means the same thing it always has. The standard deviation means the same thing it always has. So now I can use it for, and you can go back and use this unusual idea on the stuff we've done before. So we got in the middle is the mean. That's where I expect it. I expect it to be something close to this. I expect the number to be close to that. Just like Shaquille, I expect him to make close to 6 free throws. If he made 18 free throws, I go, holy crap, this is a good day for you. It would be unusual, right? So this idea goes perfectly with the math. If I go 2 steps up, so add 2.382 and then add another 2.382, where do I end up? 11.4, something above. And if we go down 2 steps, 1.9? Uh-oh. Ascension in the ranks. Yeah, so 6.688 minus 2 of these. 1.924 length. So that is what I would expect. That's what usual, from like 2 to 11. If I had somewhere from 2 to 11 out of 44 San Diegans who smoked, that would be what I would expect. So if I saw 17, would that be unusual?
Yes.
Yes. So this kind of, you see this all the time. Now here's one place where you have to be careful. This is used very often to figure out if there's any cancer-causing agent. So if you saw a little town, and you know the probability of cancer and so forth, so you do all this study because you know the probability of success. In this case, the success would be cancer because that's what you're looking for. Probability of failure, you have so many people in the town. How many do you expect to have it? If there's an unusual number of cancer cases in this little town, what do you want to go in and look further at? Maybe you want to talk to the people. Of course, I'm thinking about like Aaron Brockovich in my head right now. If you ever saw that movie. PG&E? No? You want to go talk to the people. You want to see, is there anything in the surrounding areas, their factory that might be putting stuff in the water? You want to check it out. But the probability is there's going to be some small towns that will be outside of this region just naturally. That's the thing about statistics that people don't get. Just because it's unusual, does that mean it will never happen? No, but it is an indication that there's something I should look at closer. So that's what unusual really means. It doesn't mean that something's definitely going on. It just means that I got to look closer at that because it's outside of what I expected. If you catch a fish in a lake and the fish is 7 foot long and it's supposed to be a guppy or something, you're going to want to, am I near a nuclear reactor? Something happening. Do you want to cook that fish and eat it? Probably not. All right. Cool. So that's section 4.3. So yes, I do want you to use the formula that we came up with today. Right? The book actually does not reference this formula. This is one place where I disagree with the book. The formula is remarkably simple to understand. and to put together. Okay. Oh, cool. So one last little couple things here. What's up? So, like I said earlier, we're going to make this transition from the XP of X and the NPQ, the discrete distributions. We're going to make a transition into the continuous distributions. Right? Let me start off with the simplest continuous distribution around, which is the what's called the uniform probability distribution. That's what it stands for. It just got a little lazy. And actually, let me ask you this. Let me start off with this. Any of you guys play darts at all? Anybody play darts? Throw darts? Do you know what darts is? Anybody know what darts is? Anybody not able to raise their hand? Let's see, where's my real smart ass? There you go. I knew you would do it. All right, so got to double check if there's any more smart ass than that. There's another. All right. So if you're, everybody should know darts. You know this thing in here. All those little regions and whatever. Blah blah. I'm not going to draw all of them. Let's say that there's 20 of these little regions around the edge, and they're just all shaped like that little triangle, right? You guys kind of with me so far? Okay. So it would be roughly. Somebody do this for me. What's 1 divided by 18?
0.0555.
All right, let's just pretend like this is 6% of the whole thing. Well, I guess we could say 5% to make it 100. So if there's 20 of these around, and let's say they're each almost 5%, and they got this little ball in the middle. Let's not worry about it. Let's pretend like he's not there. So you got these running around. They're all the same size, supposed to be. Don't look too much at my picture. Right, so the area of one of these is 5% of the area of the whole thing. And let's say I throw a dart, I'm blindfolded, and I throw a dart, and it hits the dartboard. What's the probability that I hit here?
0.05.
Yeah, 5%. Are you guys with me? Is that an amazing thing I've just done? No, right? Though for me, if I actually hit the board, that would be amazing, to be honest. I have to get a few drinks and I get better. But the probability that I hit this, it's related to the what. Now here's the new thing. This is something that sort of was in the book in a few little places with the spinners and stuff. But we're going to talk about it much more directly. The probability that I hit, this is going to work. Let's say that it's impossible to not hit this dartboard. Like there's this tube that's down here. And if I might hit the side and then it comes back up and it hits there. So it's impossible not to hit. So what's the probability that I hit the dartboard? 100%, because I just said it was impossible to not hit the damn thing. And so when I break it up, there's a 5% chance I'm going to hit this because this area is 5% of the whole area. So if I draw a picture that represents a probability distribution and the whole thing is an area of 1, and I have some question, what's probably it's in here, it's related to the area of that question. The hell do I mean? I don't know. So if I have what's called a uniform probability distribution, it will look like this. Maybe it could be from like, say from 5 to 10. Now somebody help me out. This is old news. How tall does it have to be so I have an accurate probability distribution? Meaning the whole area must be 1. Well, how wide is it? 5. So how tall must it be so the area is 1? Of course, the area of a rectangle is how found? How do you find the area of a rectangle? Length times width, right? So 5 times what is 1? What's the reciprocal of 5? 1/5. So however wide it is, it's got to be 1 over that tall so that the whole thing has an area of 1. So what I'm trying to get you to realize is when I have a continuous probability distribution, again, remind me, what does that word continuous mean? Does it go 5, 6, 7, 8, 9, 10? And that's it? No. What could happen? 5.5, 5.49876433961, and then sound like an auctioneer. Right? I mean, that could happen because it's continuous. Every value in between 5 and 10 can happen. So what's the area of that line? What's the area of a line? What do you think? How wide is a line? Not at all. It's not 1 because then it would be a little rectangle with 1, right? Don't kid me. How wide is a line? A line is 0 wide. So any line has an area of 0. So the probability would be 0. So what's freaky is if there's an infinite number of things that could happen, what's the probability that any one of them happens? Basically 0%. Now to be honest, let me see if you guys are still with me. I'm going to go a little bit freaky like I always do. There's a little number called iota. Sort of like the inverse of infinity. What does infinity mean? Just keeps getting bigger and bigger. It doesn't stop. It's like some people call it the biggest positive number. Well, why does that not make any sense? Because it just keeps going. So in the same sense, iota would be the smallest positive number. And that's also the incorrect way to say it for the same reason, but it's as close as you can get to 0 without actually being 0. But essentially we just say that any specific value has a probability of 0 to most humans, right? It's 0.000, 1,014 zeros, and then 1. Oh my God, that's freaking 0. All right, now, so if I want to know what's probably that it's between 6 and 9, all I have to do is figure out the area of that. And what is the area of that? Yeah, how wide is it? 3. Times, how tall is it? 1/5. So 3/5. 60% chance. Same thing as that dartboard. Why was there a 5% chance it was going to hit that? Because it represents 5% of the total board. So the area is directly related to the percentage, which is directly related to the probability. They all mean the same thing. So if I draw a picture, this is the easiest picture there is. Uniformly distributed. Everybody's got an equal chance. So the areas are all rectangles. That's beautiful. Maybe. Yes. Oh, you're good.
So percentage is related to area is related to probability.
Well, yeah, area is related to percentage. Like that's 5% of the whole area, and that's related to probabilities. I like it. How are we doing there? Are we decent there? I mean, does the dartboard idea make sense? I mean, that's where I kind of go to. Even if you don't play darts, you've seen them. You know they exist. Okay. So real quick, what would be the probability here that I get 5.102 to 7.89? Because this is continuous. It could be any number in between 5 and 10. Yeah, 2.788, 2.8, 56%, yeah. So roughly 56%?
Yeah.
Like 55.7, okay. How did we get that? We did this minus this to see how wide it was, times the height. I mean, let uniform distributions, let them be that simple. Allow them to be easy. Okay, I like it. So, what if I didn't have a uniform distribution? What if I had a normal distribution We know some about it. We know that within 1 is how much? 68%. But I'm going to want to know, what's the probability somebody's height is between 1.4 and 2.1? I want to know this area there. Now, why is that area a remarkably difficult area to get? Is it a rectangle? Is it a triangle? Is it a circle? It's an ugly thing. If anybody taking calculus, that should look like a calculus problem. Because what do you learn in calculus that does areas? You're like, I didn't know there was going to be a quiz about calculus.
I don't know what it's called, but you have to do little like boxes. Like,
3 months on.
Yeah.
Oh, are you in calculus right now? Is that what's going on?
No, I took it last year.
Last year.
Yeah.
Oh shit. So it's the integral. Now the rest of you guys, I'm sorry. You're not going to have to learn calculus. All right. We're going to stand on the shoulders of people that know calculus. There will be a little chart that I'm going to bring you. And the chart, what I'm going to be able to do with the chart, guys, hey, so no, I'm not going to teach you calculus. Don't worry about it. Unless you take my calculus course, then I will. So I want the probability between 1.4 and 2.1. That's basically impossible for us to do because that shape doesn't have an area formula. The only reason I mentioned calculus is just to let you know one thing calculus does is it's able to find the area of anything, no matter what weird ass shape it's got. It can find the area underneath any function. So people that know calculus, they did that for us, and there's going to be a table that we can look the values up on. So we can look up 2.1, we can look up 1.4, and then we can find the area between those two. So that's what we're going to be doing next, because this would be related to if I knew the average height of men, how tall should I make my door if I only want 1% of all men to complain that it's not tall enough? Then I can say, okay, well, 1% of men that are too tall would be up there. So what's this height that relates to that? Oh shit, I can't do that because it's not part of the empirical rule. I'm going to have to look it up in the chart that I'm going to give you. All right, so that's where we're going next. And I think that's plenty for today. Yeah. That is so much plenty for today. All right, anybody not get their quiz back? Yep. Everybody got the quiz? Okay.